Ideal gas is a model to simplify the problems with gas behavior. In this model, the gas molecule of an ideal gas assumed to be small enough, with a negligible volume and very far apart. The molecules are in constant random motion. The collision between molecules and collision between the molecules and the wall of the container are elastic collision. No intermolecular interactions or interactions between molecules and the wall. The ideal gas law holds that PV equals nRT, P pressure of gas, V volume, and moles of gas are gas constant with the value changes with units. Usually 1.3145 joule per K per mole is used in most calculations. Take out the unit of this constant in your calculation and T, temperature in Kelvin. In a gas mixture, the partial pressure of A is defined as Pa equals moles of A divided by the total moles of the mixture times the total pressure, or rewritten as Pa equals nRT over V. The total pressure of the mixture is the sum of all partial pressures of the components. Question: when you collect the oxygen gas over water, the gas you collected is a mixture of oxygen and water. If the partial pressure of water is 3.16 kilopascal at 25 degrees C, how many moles of oxygen in 1 liter of mixture, given the pressure is 1 atmosphere? During the collection of oxygen, the water vapor will also fill the container. The container has a mixture of oxygen and water vapor. According to the definition of partial pressure, we have the total pressure, 1 atmosphere, equals partial pressure of water vapor plus partial pressure of oxygen. We have to change the unit because 1 atmosphere is equivalent to 101.33 kilopascal. We have 101.33 kilopascal equals 3.16 kilopascal plus P oxygen. And P oxygen is 98.17 kilopascal. Then we can use the ideal gas law. PV equals nRT to calculate N. The moles of oxygen, N equals 98.17 times 1.0 liter divided by RT. The final answer is 0.0396 moles of oxygen. Ideal gas model is very successful, but the errors introduced by neglecting intermolecular interaction and the size of the molecules are very high in solving practical problems because there are intermolecular interactions in the real gases. The volume of every single molecule cannot be neglected. Van der Waals equation shows you how to correct it. 2 correction terms are plugged into the ideal gas law. 1 for the size correction, 1 for intermolecular interaction correction. And the parameters A and B can be found in the data manual. We can use it for real gases.